This is the field of a dipole. Now what we are interested is, if this field of a dipole, okay, or if this dipole exists and we apply an external magnetic field, will there be a force on the dipole? Okay. It turns out that there will be a force on the dipole and we want to calculate that force. Okay. So assume that we have a small dipole in the form of a loop carrying a current I. Okay. Now I am going to apply a magnetic field at a uniform magnetic field of value B external, okay, and this angle that it would make with respect to z axis will be theta. What happens physically is that the loop starts to align itself along the direction of the magnetic field, and we want to show what would happen there or what would be the reason for that. Consider a point, any point over here, okay. So there is a current that is going through this, so there is going to be a current element IDL, right. The current element is IA d phi hat. Of course I will also replace this phi hat by cos phi y hat minus sin phi x hat in the xyz coordinate system, and then I ask for what is the magnetic torque at this point. Okay, so if I call this point as P, I want to find out what is the torque at that point P. Okay, torque I know is given by R cross F, right, where R is the vector which is drawn from the origin, the fixed point, to the point where I am calculating the torque. So if this is the origin, this is the vector R, and you know, it's like I am applying a force up here. What is the force at point P? Multiplied that by the cross product of that with respect to R, because only the force that would be perpendicular to this R direction would result in the movement of rotation, otherwise it would not rotate, and torque actually measures how much rotation is possible. Okay. So the torque dTm at the point P is given by R cross dF, and this force is because of the magnetic field that we have applied, because of the external magnetic field that we have applied. So this becomes dFm. Okay. So now let me write down what is R here. R is A cos phi x hat plus A sin phi y hat. Okay. What is the magnetic force dFm at point P? The magnetic force is IDL cross B, correct? B is the external uniform magnetic field that we have applied, and IDL we have already written as IA cos phi y hat minus sin phi x hat, okay, cross d phi will be constant, so that I am going to write down later. So let me write down this IA cos phi y hat minus sin phi x hat cross with B external. B external field can be written in terms of its x, y and z components. So I have x hat Bx plus y hat By plus z hat Bz. Okay. This entire thing multiplied by d phi. So I am going to write this as Ia d phi, and this is the expression. Now you have to recall the cross product formulas, right, or you can see that one. Y cross x will give you minus z, y cross y will give you 0, y cross z will give you x component, x cross x will give you 0, x cross y will give you z, x cross z will give you minus y. So if you do all this cross product, you can see that the torque, if you substitute all these expressions into the torque, you will see that the torque becomes Ia square d phi, okay, times Bx cos phi plus By sin phi multiplied by minus sin phi x hat plus cos phi y hat. I will leave this as an exercise to you to show that this is the expression for torque that you are going to obtain. This involves lot of cross products. It's not difficult. It is very easy to do this, except that it's tedious, and to show all the steps would mean we are going to be distracted a lot. So I will leave this as an exercise. You can show that this is what it is, and you are not interested in the differential torque, you are actually interested in the total torque. So in order to obtain the total torque, you need to integrate this one, implies integrating over d phi from 0 to 2 pi of this expression, right. So you can put this expression and integrate over 2 pi. Again there are 4 terms here, cos phi, sin phi, cos phi, cos phi, sin phi and sin phi cos phi. The cross terms cos phi, sin phi and sin phi cos phi integrate to 0, leaving behind only two other values, which is given by pi a square I, okay, minus x hat by plus y hat bx. Again, if you recognize pi a square as the area of the loop, okay, that we have considered, the area of the loop S, then this quantity I into S is the magnetic moment M, and if the magnetic moment M is directed along Z direction, so that would be the vector magnetic moment M, right. And if you do this vector magnetic times the B field, B external field, you are going to get this expression in the top, okay. And instead of writing this as mz prime z hat, it is customary to write this as m cross B, okay. So this is m cross B, because the loop can have any direction, the magnetic moment of the loop can be directed in any way, but as long as the field is uniform over the loop, and this is important, you are not considering loops of radius kilometers, okay, you are considering loops of very very tiny radius over which the magnetic field is going to be uniform, then the torque, magnetic torque that is produced because of the magnetic force is given by m cross B, okay. So this expression is very important because we are going to use this expression later, okay. So this torque, because of the magnetic moment M, which could be directed anywhere in the space, will be m cross B, okay. So the torque will be in the plane that would be perpendicular to both M and B, okay. If you take a compass needle, okay, which could be considered as a dipole, right, and you place it anywhere, okay, it would point in a certain direction, okay. This is your earth, okay, or this is my earth as well. So this is earth. Earth has magnetic field which can be thought of as a big bar magnet of magnetic poles south and north, except that the geographic north is located at magnetic south and geographic south is located as magnetic north. Of course, this magnetic pole itself actually reverses direction every few thousands of years. So for the current era in which we are living, the south pole of the earth magnet coincides with the geographic north of the earth, and similarly north pole of the magnet of the earth coincides with the geographic south pole, okay. So because this is a dipole, essentially there will be field lines around it, and the field lines would be going from north to south poles, right. So this would be the field line at a far away distance. So the field line actually goes through somewhere over here, and then there are field lines surrounding this. Now because there is a field here, and if I now take a compass and then place the compass here, the compass would actually point to the north, okay, because the magnetic moment would affect it in such a way that the compass would actually point to the geographic north, because it would be aligning in the opposite direction to the magnetic field B. So it would point in the direction to the geographic north, okay, and that would be the magnetic field. Of course, the dipole itself is taken from south to north, right. So in our notation the dipole was taken from south to north, and for the compass it points to the geographical north, okay. So this with a fictitious charge of Qm and minus Qm, if you can think of, or you can think of this as a small bar magnet. You could of course also think of this as a small loop of a certain radius and carrying a current Im, okay. But the important point is that this compass always points to the geographical north. Why it is pointing to the geographical north? Because that is where the south pole of the magnet is located. So it gets attracted to the south pole of the magnet. But because south magnetic pole is actually north geographic pole, we say that compass seeks north, okay. So if you take a compass which can be freely rotated, if you place this one, it would always try to point to the direction of south magnetic pole. After a few thousand years, our next generation people would actually see that the magnet would seek south, okay. This is a slightly simplified result because the actual poles are not aligned directly to the north or the south geographic pole, but there is actually a small amount of declination over here, okay. So there is a small amount of declination which is about 12 degrees, okay. The south pole is around 12 degrees declined with respect to the north geographic pole, and the north magnetic pole is 12 degrees declined to south geographic pole, okay. So when you design a compass, right, you will have to consider this declination and then compensate for that declination. It would actually point to this 12 degrees, then you have to apply an additional force so that it would actually point to the proper geographic north pole. Okay. So, this was the force on the dipole. Before leaving these forces, there is one last thing which I would like to talk about, and that is force on two wires. Okay. Let us assume that there are two wires I1 and I2, okay, and these wires are carrying currents in the same direction. Okay. So, this is Y and this is X. I want to find out what is the force on this wire I2, okay, at the point here. At this point on the Y axis, I want to find out what is the force on the second wire because of the force due to the first wire, I mean because of the current in the first wire. Clearly there will be magnetic field lines around this, right. So, there would be magnetic field lines and there would be a magnetic field that would be passing through this 0y0 point. Okay. If I find the magnetic field there, it would be along the direction minus x, right. You have to imagine this slightly. So, the magnetic field here would actually be pointing in the phi direction, but at phi for y axis would actually be pointing in the minus y direction. Okay. So, what would be the magnetic force there? The magnetic field at this point, call this as B1 at 0 y0 due to I1 points along minus x direction, which is actually the phi direction for that, but on the y axis phi is directed along minus x direction, right. So, go back to cylindrical coordinates to really understand this statement. So, there will be a certain force that this point experiences or this wire experiences, and that force is given by approximately given by I2 dz, which is the current element located at that point, I2 dz with a very small height z, and the current element is pointing along the z axis cross minus B1 x hat, B1 being the magnitude of the magnetic field because of the current I1, and it is directed along minus x hat. So, this would be the infinitesimal amount of force that this gets experienced, right. So, you can write this out as dF2 is equal to I2 B1 would come out. What is the magnetic field B1? B1 is mu 0 I1 by 2 pi y, correct. This is the magnetic field because of the current in the wire I1. So, this would be I2 mu 0 I1 by 2 pi y. What would be the direction of this force? This is z hat cross x hat. Z hat cross x hat will be along y direction, but there is a minus sign here. So, this would be along minus y hat. Okay. So, let me just emphasize that the direction is along minus y hat, and the magnitude of the force, the infinitesimal force is I2 mu 0 I1 by 2 pi y. So, sorry, there is a dz over here. So, let us write down that dz. So, if you evaluate what is the force per unit length kind of a thing, then the force per unit length is I1 I2 mu 0 divided by 2 pi. The force per unit length I want it at 1 meter. So, this would be 2 pi itself at y is equal to 1, and it would be directed along minus y. If further I1 and I2 carry a current of 1 ampere, okay, then this would actually be the expression. That is, if the force per unit length is 1 Newton per meter, then I1 and I2 would carry, and if they are equal amounts of current, then that would be the definition of ampere. Okay. And the direction is minus y, indicating that this wire actually bends or experiences a force towards this wire I1, right. So, wire carrying the current I1. So, there is essentially a force of attraction between two wires, and instead of current I in the direction which is same as I1, if you had a current which was in the opposite direction, then there will be a force of repulsion. So, two wires carrying current in the same direction get attracted to each other, two wires carrying currents in the different direction will repel each other. Okay. So, this is the force and the definition of ampere, which is the internationally adopted definition for current. Okay. So, we discussed force. There is one last thing, although I said last, but I would like to talk about this effect, okay, which is important in semiconductor devices. This is called as Hall effect. Okay. What is Hall effect? It is simple. You take a conducting material, even if it is not perfectly conducting, do not bother, it is alright. You take a material, okay, there must be some way of some amount of current it must sustain. So it could be, for example, a semiconductor bar, okay, having a thickness T and having a width W, and it is uniform in the Z direction, if I am going to assume that one. And I can force a current through this, okay. Let us say I force a bias current of I0 through this one, which means that there would be charges which would be flowing. If the semiconductor bar has holes, then the holes will be flowing along this direction I0, the electrons would be flowing opposite to I0, okay. Now you have, let us also put down the axis to the top is Z, this side of the axis is Y, and the direction of the current is X, okay. Now what I am going to do is that I am going to apply a magnetic field which is uniform throughout and having a value of B0 and directed along Z axis. That is, I am going to apply a magnetic field perpendicular to the bar, and I want to find out what happens to this. It turns out that because of this magnetic field, there will be a charge separation leading to a voltage difference between the two ends, two faces of the bar that we are considering, a conducting bar that we are considering, and this would produce an electric field which in turn will produce a voltage between the two faces or the two ends of the bar, and this voltage is called as the Hall voltage, and we are going to discuss what is this Hall voltage, and this element itself is sometimes called as a Hall sensor, okay. So we are going to discuss that one. So we have applied a magnetic field B, okay, it would be pointing in the direction Z, which is coming out of the bar here in the normal direction. So what will be, first let us look at what will be J, okay. The current density J will be in the X direction, correct. Current density will be in the X direction because the current is actually going along X. So you should actually imagine current lines I0, uniform bias current lines like this, and therefore J vector will be along X direction. What is the current density there? The magnitude of the current density is whatever the current total current I0 is divided by the area. And what is the area? The cross sectional area through which these lines are coming out is W into T, right. So this is the cross sectional area that they are coming out, and this has W and T, right. So width of W and thickness of T, and this is the magnitude of the current density, and the vector current will be equal to I0 divided by Wt into X hat. Now the idea will be this: there are these charges which are constituting the current, and they would be flowing in this direction I0 or opposite to I0 depending on the type of the charge, but the presence of the magnetic field will now exert an additional force on them, and we want to calculate that additional force. We already know what is the force exerted because of the magnetic field, that would be Q into V cross B, right. I know B is directed along Z direction, I do not know what is V, I want to find out what is V, and to find out V, recall the relationship between J and V. J is given by the volume charge density rho V multiplied by the velocity of the charge carriers, which is V bar. So if I know J, I know V, if I know V, I know Fm, if I know Fm, then I can find out what is the resultant force. From the resultant force I can know what will happen to the charges. This is the goal, okay. So first find out, so this is my first step, this is my second step, and third step would be to evaluate the total force on the charge carriers, okay. So using this expression, I know what is J, I can easily find out what is V. V is given by I0 divided by Wt rho V going along X direction, okay. So I have completed the first step. So what would be the magnetic force? Magnetic force will be the charge carriers experience. Since this is not a single charge but rather a charge distribution, I need to modify this equation slightly. This becomes dFm, the infinitesimal force that this experience, or the force that is experienced by the charge carrier, that would be in place of Q, that becomes rho V, correct. So the magnetic force, the differential magnetic force, or the magnetic force in a sense that the charge distribution experiences, is given by I0 divided by Wt. Rho V cancels out because rho V is in the denominator, rho V is in the numerator, that goes away. So I have X hat cross B0 Z hat gives me I0 B0 divided by Wt, okay, and X cross Z will be along minus Y direction. What's interesting to note is that this force that we have obtained is completely independent of the type of charge carrier. independent, I am going to write this one down to emphasize this, independent of polarity of the charge. Both positive charges as well as negative charges, that is positive charges in the form of holes and negative charges in the form of electrons, will experience a force along minus y direction itself. So if you look at the total force this is experiencing of the bar, you see that this is the bar that I have. Okay, let us imagine for a moment that there is a positive charge carrier over here. There is already a force because of the electric field, because of the bias current, there is already a electric force due to this. The electric force is directed along x direction, correct? Now, or the differential force if you want, okay, this would be the differential electric field, differential electric force that is experienced. But there is also a force because of the magnetic field, and that would be directed along minus y direction. This would be the magnetic force dFm. What would be the resultant direction? Resultant direction for this charge carrier will be along the midway between dFe and dFm, and it would actually push the charge to the edge of this bar. So you can actually have charges anywhere over here, and these charges would actually be pushed to the edges and essentially line up on this left edge. Okay. If instead of this charge I had a negative charge here, now the negative charge experiences an electric field in this direction, right? This is the electric field for the negative charge carriers or the electrons, because electrons move in the opposite direction to the field, whereas magnetic force is still in the same direction. So what will happen to the resultant field? The resultant force will be along this direction, okay, which means the charge actually moves to this edge. So there is charge here which gets lined up, okay. So you have what you have done is to essentially create a charge separation. All the positive charges are lined to the left, all the negative charges have been moved to the right. Because of this there will actually be an electric field inside, right. So there will be an electric field inside which would be directed in this way, and this electric field will create a certain potential difference if you apply, okay, if you connect two conducting wires to this, you will see that there will be a potential that is developed, okay. So you will see that there is a potential developed, and this potential is called the Hall potential. What is the potential? Well, first we need to look at what is the electric field that is developed, okay. The electric field that is developed must be such a way that it actually opposes whatever the magnetic force is, because it has to create a magnetic force, it has to create a force balance, so it would actually be enough to oppose the magnetic field. So for electric field is force per charge, so this would be minus dFm divided by rho v, correct. dFm being the magnetic force divided by rho v, and this minus sign because the electric field, because of the Hall effect, has to oppose the magnetic force, right. So if you substitute expression for dFm and carry out the simplification, you are going to get the electric field as I0 B0 divided by Wt, rho v is there, okay, times y hat. This is correct because the electric field is directed from the positive to negative charges. I am getting the Hall electric field also directed along the positive y axis, and this is alright. So what would be the Hall voltage? Voltage will be electric field times the width, or the integration of the electric field from point here onto the left to the point on the right. So this would be the Hall voltage, and that will be equal to the electric field, fortunately is uniform here, or in the case that we have considered, this would be the Hall voltage into W, that is given by I0 B0 divided by rho v thickness T. This is the Hall voltage, and it is very, very important. Why? Because if you look at the Hall voltage, it actually depends on rho v, and we know that if the bar is made up of entirely positive charge carriers, okay, then the Hall voltage will be positive. If the bar is made up of negative charge carriers such as electrons, then the Hall voltage will be negative. So if I want to test a bar, whether it is p type bar or an n type bar, then it is very easy for me to do so, right. I establish a certain bias current, and then I connect two conducting wires and put a voltmeter over here, right, and then apply a magnetic field which is uniform in normal direction to the bar, and I will see the polarity of the voltage. If the polarity is positive, then I know that the charge carriers are all positive, otherwise I know that the charge carriers are negative. In fact, this was used to establish the fact that there are holes and holes are positively charged by early semiconductor people who conducted these experiments. And these Hall sensors are actually available, which do not actually require an external magnetic field. Earth has a magnetic field, so you take a Hall sensor, place it on Earth, and then that Earth's magnetic field itself will do the charge separation and then generate a Hall voltage. Okay, that can be used in fact to measure the magnetic fields as well. So this was to kind of find the charge distribution, but you can turn it around and say I know what the charges are. Let us say I just take a piece of metal, then I place it in the magnetic field, then the charges, I mean the Hall voltage would be of a certain polarity, and the magnitude of the Hall voltage depends on the magnitude of the magnetic field. So assuming that this magnetic field is uniform, I can actually find out the magnetic field itself. I can measure the magnetic field. Okay. So this was what we wanted to discuss about force and torque on the dipoles because of the magnetic fields.